Hello, my name is David Goedicke, and today I will present the paper XR-OOM Mixed Reality Driving Simulation with Real Cars for Research and Design. The work was jointly done with Cornell Tech and supported by the Toyota Research Institute, and done by myself, Alexandra Bremers, Sam Lee, Frank Bu, Hiroshi Yasuda, and Wendy. This work mostly tries to address some limitations of lab-based studies, like the limited sense of motion that often lab-based simulators have, or the limited screen space that they have available, and also offer new avenues for research and design development. In particular, designing interfaces, new car interiors as the participant is driving in a vehicle, autonomous vehicle behavior designs, if, for example, the participant is driving as a passenger in a fake autonomous vehicle, and then experiencing various scenarios and leading to the next point, unusual traffic scenarios. This method really gives us a way of looking at these things from a much more sort of broader perspective, and unbound by real-world scenarios that frequently occur, even though we're still driving in a real vehicle. We are not the first ones to do this kind of work. Volvo in 2020 published both a video and a workshop paper on using such a system, where they demoed how a car interior could be changed. However, for this method really to become fully useful and gain a similar status as established in-lab methods, there are a couple of additional aspects that we need to evaluate. In particular, safety. How do you operate a simulator safely and make sure that nothing happens where the participant will have, drive away or just trying to drive while the headset shuts off. Other aspects are participant comfort. After all, the participant is seeing the world through a mixed reality headset as they're driving or as they're moving around. That could be very nausea-inducing, so that's very important. And finally, we want to understand what it actually means to measure driving performance in this way. What are aspects that are similar, and what are maybe kinds of conclusions or results that we shouldn't draw from this kind of method. A quick technical overview. We used the Vardro XR1 as our mixed reality headset. We had a Smart Track 3 tracking this XR1 within the car as the participant was moving their heads, and the Z2 tracking the vehicle itself. We had a secondary system tracking the car in motion as well, which we mostly used as a way to compare the performance of our virtual reality system. Before we get to driving tasks, one other set of tasks that we also evaluated were cockpit tasks. They're almost equally as important as they enable participants a good view of the surrounding and so on. And so we wanted to make sure to also include these steps in it. Many of these points were not a problem at all. However, some taller participants had problems with bumping into the car as they were wearing the headset, as it is still relatively bulky. One point almost every participant had a difficult time with was the very last one, where they were asked to verbally explain the indicator lights that are visible. And as we can see in the next clip, this turned out to be a problem for many participants due to dynamic range issues of the cameras and how it was trying to auto-expose, as well as aliasing with the refresh rates between the display and the headset's cameras.
Under leg, I can see that I've engaged it, and I've disengaged it, verbally explain which indicator lights are visible. Indicator lights. I assume like up here, I can faintly see 0 miles per hour. I can make out it to be fuel. Time is 2:28. Fuel is full. I cannot read what's on the right there. I cannot read the small engine light or any of that to the left of the miles per hour.
The second task then of our experiment was to evaluate the driving performance of participants. And in order to remain in a safe environment, we made sure that these were all tasks done at a low speed on a parking lot separated from regular traffic. In this parking lot, we laid out a couple of traffic cones as laid out on the pattern, and then had the participants drive through them in these 4 different steps. Sometimes these cones were physical cones, and sometimes those cones were virtual cones, so we could compare between the different conditions. In the following video, we will show a participant driving through one of these environments. Very important to point out here is that with the camera setup as described in our paper and visible here, we can actually capture the entire environment. In the top left corner, for example, you can see the outside world as the parking lot where we were driving in. On the top right side, from the same 360 camera, you can see the participant and how they are acting in the vehicle or operating the vehicle. On the bottom left side, you can see the participant's point of view, exactly the things that we were rendering to the headset. And then on the bottom right, we have the output from the tracking algorithm showing us where the car is moving relative to the virtual world.
Alright, I need to back up a little.
In general, we could show that driving is actually not a problem and works in these kinds of setups. However, cockpit tasks, or in particular some cockpit tasks, were more difficult and could use some technical improvements. Additionally, reversing and having mirrors that also work with virtual objects were very challenging. Originally, we wanted to have the participants parallel park, which we had to exclude due to the limitation of not being able to see in mirrors or back driving cameras. The localization could be improved to allow for higher speeds. The driving performance measures that were recorded could also be much more analyzed, like steering wheel angles and throttle input from the canvas of the vehicle. And finally, there are a few headset limitations, like the weight of the headset and its relatively slow auto exposure adjustment could be improved so that like the high dynamic range between switching, looking at the speed and looking at the real world could be improved so that once you look from the internal dashboard outside, it's not all just white and blown out. Finally, I wanted to thank everyone. I wanted to thank you for watching and listening. I wanted to thank the team for working on this project and the other members of the lab who also helped. If you want to get in contact, feel free to send me an email or try to contact me on GitHub. And again, thanks goes to Cornell Tech and of course the Toyota Research Institute for supporting and funding this work. Thank you so much.